Hello, hi everyone. Welcome to this session on computer vision. Computer vision is a part of AI which actually delves deep into the mechanism of how computers were able to see the objects and were able to identify what the object is and take actions accordingly. So this is a section which will delve deep into the vision which computer got and how they got it. So we will move ahead. So our agenda for today will be as follows. We will explore the field of computer vision, how the computer started seeing, and how it has revolutionized the whole world around us. We will deep dive into various computer vision technologies and understand the business cases which are transformed by computer vision. So we will see what computer vision is and then what all are the various options in computer vision like image classification, object detection, then optical character recognition, image segmentation, image tracking, post detection, image generation, and image pre-processing. So these are all the various different aspects of computer vision, which we will look into detail. Then we will explore how we can do EDA on images and then the business cases. So computer vision is the field of AI which enables machines to interpret and understand visual information from the world, just like human eyesight, but through algorithms and mathematical models. So how the human vision is? The human vision, when imagine you close your eyes for just a moment, when you open them again, something extraordinary happens. Your brain instantly processes the visual world around you with remarkable speed and accuracy. This magical ability to see, identify, understand, and react is exactly what computer vision tries to give to machines. So, object recognition is identifying what the object is. Like this is a chair. Then, face identification. This is my friend. Scene understanding. This is a road. Motion tracking. The ball is coming towards me. Text recognition. There is text written here. So, this is exactly like how a child learns to see. The child is exposed to various examples and then it slowly does the pattern recognition in its mind. And next time when they see a real cat, they shout, "Look, cat." Then comes the refinement. That is understanding big cat, small cat, cartoon cat, etc. So how computer vision works? So basically computer understands everything only in pixels and numerical values. Okay. So it doesn't actually understand what the object is, but it is able to convert the object into a map which it is able to correlate with the object. So just like your eyes capturing light and forming an image, the computer receives visual input through camera or image files and then they break it into patterns. So they analyze the image, they look for fundamental visual features, the edges, colors, distribution across regions, geometric shapes, and then these patterns are matched to its knowledge base. So they try to look for the edges and shapes which they have seen before, which is stored in their knowledge base. And based on that, they predict that, okay, this is a dog. And they predict with some confidence level because the patterns which they are able to match with their internal database. So it comes to some percentage. It may come to 95%. It may come to 85%. So this is how computer vision actually works. So if we take an example, Tesla's autopilot, computer vision is the key behind Tesla's autopilot project. So Tesla cars are able to navigate through the road without any human intervention. And even if suddenly someone comes on the road, they are able to apply brakes within milliseconds. So how all this happens? Because they have cameras. The cameras are their eyes. There are camera which give them 360-degree vision. Then there are computer vision models which actually parse the image which the cameras take and then they try to understand what those objects are. And then it has a deep learning neural brain, which actually tries to identify what needs to be done next based on what the car sees. So there are road detection, then vehicle tracking is there, traffic signals are there, lane recognition, pedestrian safety. So all this is possible through computer vision. Banking and financial security. So here computer vision plays a key role. Name verification, confirming the account holder's name matches the record, signature matching, amount validation, document authenticity, checking for proper watermarks and security features, and detection of tampering. So computer vision is able to do all of these. It is able to extract text from the image, and then it is able to check that text across what is stored in database and then find out whether it is matching or not. It uses patterns to match the signatures against the database where the signature is already stored. So basically, it becomes a digital bank officer's eyes, processing thousands of checks per hour with consistent accuracy and catching fraud which human eyes might miss. Image classification is the foundational task in computer vision, where actually a model sees an entire image, studies its patterns, and then assigns it to one single category as to what this image is, right? So how it works. The CNN vision transformer models, they extract the hierarchical features from images, starting with simple edges and shapes, progressing to complex textures and patterns. And this is given to the output. The model returns a single label for the entire image based on the patterns which it matches, which it with its training which has been done, and then it says that this is a cat, dog, or a tomato leaf with particular disease, or if it is an Aadhaar card. So if you see the real world application, plant disease detection, automated sorting of goods, medical x-rays, all these are the real world applications of image classification. What is this overall photo about? That is what is the key analogy. So here it classifies the image. So if you see the analogy, it is like a child learning to recognize objects, how humans learn. So when you show a lot of photos to a child and every time you tell the child, this is cat, this is cat, this is cat, this is dog, this is dog, then that is where the child is able to understand that, okay, if the patterns are in such a manner, then this is dog. If the patterns are in a different manner, this is cat. So that is how image classification works. We show the computer hundreds of thousands of labeled images where we have labeled the image whether it is dog or cat. And computer learns the hidden patterns, the shapes of ear, tail positions, fur textures, nose structure, body proportions, and all these are learned and then stored in their models. So next time when an image comes, it is confidently able to tell whether it is a cat or a dog. If we take another example, it's like out of the bunch of all the clothes which are lying around, you are able to quickly pick out shirts, socks, and jeans and classify them into different buckets. So this is exactly how image classification works. So you give an input image, then there are feature extraction which happens. So the edges, textures, shapes, everything is extracted and then stored in a database. And then pattern comparison happens. So it is compared with the values on which the model is trained. And then finally it predicts based on the best matching category with a confidence score. So what are the benefits? Lightning fast processing. Okay. So you can process thousands of images in a second, right? Enabling real-time decision making at unprecedented scale. So because now the computer is able to understand images and with a high confidence level, it can immediately start processing thousands of images through an API and start giving them labels. There is very high accuracy because we have deep learning algorithms and transformer models which actually lead to higher accuracy based on their architectures. Consistency is there, so there is no distraction, there is no emotional bias. They work 24 by 7. Massive automation can be used to reduce manual labor in inspection, quality checks, and repetitive visual tasks. And this all leads to significant cost savings and enhanced safety. Manufacturing applications. So if you see defect detection, automatically identifying scratches, cracks, and dents, and other manufacturing flaws on products as they move through production lines. Classifying finished items into quality tires, grade A, B, or C, based on the appearances and specifications. So here, image classification is used in grading the m- yeah, it is used in grading the actual product as to what quality it belongs to. So it can be grade A, grade B, or grade C, and it is all based on the features it learns. So if it is able to see some quality issues, it will label it as grade C. If there are very less quality issues, label it at grade B, and then grade A for the products where there are no issues found. So it can easily replace human in doing this in visual inspection task. If you see in agriculture, so plant disease detection, right? So by taking the photo of the plant, you can find out what the disease is there in the plant, and accordingly you can then apply the pesticides. Overall crop health monitoring can be done without any human intervention. So there are drones which go and take the visual images of the crops, and then they upload it to a server where it is compared with the database, and then we get an idea as to how much overall there is disease in the plants. Again, soil type classification can be done. So it can analyze the soil composition and characteristics from images to guide planting decisions. So these are the applications which we have for image classification. Next, we move on to object detection. So that was image classification. It was seeing the image and classifying it. Here we are trying to detect an object within an image. Okay. So it is a core task of computer vision, which empowers system with the remarkable ability to both identify and locate objects within images. So object detection combines two essential capabilities: image classification and object localization. So first it classifies the image whether this object is present in it or not, and then it gives the exact coordinates of where the object is present. So how it works? So object detection, first the image are converted to numbers, then there are features which are extracted through deep learning models, and then model scans the image using different strategies, and then there are YOLO models and other models which actually are able to identify the bounding boxes across the images because they are trained on annotated images where they already have seen so many images with bounding boxes. So if we take an example of an Aadhaar card, then in Aadhaar card, if you want to identify whether it is an Aadhaar card, is image classification. But if you want to identify where the Aadhaar number is in the image, then that comes under object detection. So the YOLO model is trained on thousands of images of Aadhaar card where it has the annotation. It has the bounding boxes for the Aadhaar card. So from there it is able to learn and creates its own database. So whenever a new Aadhaar card comes, it is easily able to locate the bounding box across the Aadhaar card. And then the final result is a clean set of detected objects with precise coordinates, which can be used further. So once you get where the Aadhaar number is in an image, then you can use other technologies to extract the Aadhaar number. But detecting Aadhaar number in an image, it comes under object detection. So what algorithms are used? So there are traditional methods. So before deep learning came into picture, SVM was used for object detection. Then we have RNN, RCNN, fast RCNN, mask RCNN. Then we have one state detector, fast and real time performance. You only look once, YOLO. YOLO is very good in object detection because it is trained on annotated data. And then next generation AI is there, transformer based models. That is DETR, detection transformer. So choosing the right algorithm is very, very important. YOLO and transformer based models are very versatile and they give high accuracy. What are the business cases of object detection across the industries? So in retail, customer counting and foot traffic analysis, shelf product detection and inventory management, theft prevention, automated billing system. Manufacturing, you can detect defects like scratches, dents, because those are objects in an image. So in real line time assembly line, you can detect where the edges are, where the dents are, where the scratches are. In healthcare, you can detect where the tumors are in an X-ray scan or a CT scan, right? You can identify surgical instruments during procedures. Autonomous vehicles, so detecting various objects on the road. So if there is a human crossing the lane, then it detects that okay, this is a in this image, this object is a human. Then detecting the traffic signs, right? Detecting other vehicles. So a lot of object detection happens in autonomous vehicles. In agriculture, you can automatically do fruit counting, crop disease detection, because in the images you find out where the fruits are as an object and then count them. In real time traffic management, if you take a photo of the queue of traffic, you can then easily detect the objects and count them, how many cars are there. In financial services, it is used in Aadhaar masking or PII masking. So you identify PII through object detection and then you can mask it. Then weapon detection, suspicious activity monitoring. So there are so many uses of this object detection method. Then next we come to optical character recognition. This is another area of computer vision where we use computer vision and natural language processing techniques to find out what is written in the images. So from the images, we extract the text, and that process is known as optical character recognition. So it can process photographs, scan documents, PDFs to extract textual content. It can recognize characters. The technology identifies both printed and handwritten characters with remarkable accuracy and then convert to digital text. How it works internally. So first the image pre-processing happens. You remove the noise, convert it to grayscale, then binarization is done. It is converted into black and white. Resizing and normalization is done. Contrast enhancement is done. So these are all the image pre-processing techniques which are used. Then comes the text detection. This step identifies text regions using advanced algorithms. There are East, Craft, DBNet, and YOLO models which help in detecting where the text are. And then text recognition. What the text means. So it converts pixel patterns into characters using CNN, RNN algorithms, transform algorithms. So these particular patterns are matched against the patterns which are stored in the model when it is trained. So from that, it is able to identify that this pattern is A, this pattern is B, and then it emits out the text from the images. So this is how OCR works internally. So there are multiple ways of doing OCR: traditional OCR, rule based, or classical methods, tesseract OCR, which has been in the industry from a long time, but it is excellent for clean and printed images. But where the low quality images are there or handwritten content is there, it is not able to detect. Then we have AB Fine Reader, commercial solution, most accurate traditional OCR engines. Then we have deep learning based OCRs, Craft, CRNN, East Model, TROCR, Donut, Easy OCR, Paddle OCR. Paddle OCR is very famous. It is used and it supports 80 plus languages. Excellent for financial documents and ID cards. Then accordingly, we have cloud OCR services where you give your image or document to the cloud and it gives you back the text. So options, a lot of options are there. Google Vision OCR, AWS Text Track, Azure OCR Layout LM, Adobe OCR. So all these are the OCR based solutions. OCR is one of the key aspects of computer vision and it is most influential in driving the transformation across the industry. So because it is able to convert the image, whatever is there in the image into text, it has multiple applications. In banking and financial services, it automates check processing, faster customer onboarding happens, fraud detection happens. In healthcare, it is better patient management and reduce administrative burden, where everything is extracted from digitized reports and then processed. In government area, it digitizes the archives, processes census forms, and interprets ID documents at scale. In manufacturing, it reads the serial numbers and automates warranty card scanning. In insurance, it automates claim processing because it is able to extract data and information and drastically reduces claim settlement time. In retail and logistics, it is able to process the invoices directly by extracting data and checking and taking decisions, detects shipment labels, recognizes barcodes combined with text. In telecom sector, it automates customer onboarding forms. In education, digitized exam papers can be scanned and then easily checked automatically. Next, we come to another area of image computer vision, which is image segmentation. Image segmentation refers to a separate area where it is able to segment the image into multiple objects. So, if there is an image of a man or a woman wearing clothes, then it can identify that okay, this part is the shirt, this part is the trouser, this part is the head where it is wearing a hat and a glass. So this is what segmentation is. It divides an image into meaningful regions by assigning specific label to every single pixel. This fundamental approach will allow machines to understand visual content at an unprecedented level of detail. So just imagine if you give a complex image to a computer and it is able to identify and segment it with all different objects. So that is what image segmentation is. It helps machine understand images with exceptional precision, right? So in medical imaging, precise tumor and organ boundary detection. So it is able to identify in the image or a scanned CT scan image as to where the organs are and where the tumors are. So these are different segments in a single image. Robotics, object recognition and manipulation, self-driving cars, road and obstacle segmentation. Then we have manufacturing, agriculture. So many applications are there. Then we have AI-powered virtual dress try-on system, which transforms the retail and fashion industry. And this is a classic example of image segmentation, right? So when you go to the online commerce e-commerce site, you can just upload your photo and then you can select the dress which you want, and it will be superimposed on your photo, and you can see how you look in the dress. This has revolutionized the whole shopping experience. The digital trailer analogy, a super fast AI trailer who is available 24 by 7. So digital transformation brings the boutique experience to every customer's device, eliminating the wait time and limitations of traditional trial rooms. So how the virtual try-on solution works. You try before you buy. Customers visualize complete outfit on their own body digitally, eliminating fit uncertainty. They get personalized recommendations. It analyzes the body shape, style preference, and suggests what are the options they can look at. Advances Advanced warping algorithms simulate how fabric moves naturally on individual body contours. So this reduces the overall operational cost. Technical pipeline. So there are 7 critical steps. User image is captured, and then human pose estimation is done. So there are multiple models which helps in estimating the pose of the human, and based on the pose and body segmentation is done later as to dividing the body into multiple parts, the upper part, lower part, and the head. Cloth feature extraction is done. Deep learning identifies sleeves, neckline, hem pattern from catalog images. And then from warping to rendering, the final stages. Cloth warping and fitting. Using thin plate, spline warping, spatial transformer networks, and Vuitton models, clothing reshapes to fit the user's exact body contours. Rendering and blending is done, which creates realistic shadows, reflections, wrinkles, and cloth body interaction. And then finally, there is a real time try on output where the cloth is exactly warped on the body, and advanced systems enable 360-degree rotation using NERF. Next, we come to image tracking. So, what is image tracking? Image tracking is basically it identifies in the image or in the frame of the image as to where the object is right now, and then in the next frame it will tell where it moved next. So how the object is moving across the various frames of images. So if you think of it in as an analogy, object detection is a snapshot and object tracking is a movie. Detection tells you what's in a single frame. Tracking tells you the story of how objects move, interact, and behave across time, creating a narrative from sequential data. Why image tracking matters? Because image tracking can be used for surveillance. It can monitor individual and detect suspicious behavior across multiple camera feeds. Autonomous vehicle. So in autonomous vehicle, there is constantly changing environment, and there are pedestrians, cyclists, vehicles. So image tracking actually helps. It is able to find out what is the next state of the image, and then accordingly decisions can be taken. Then we have sports analytics. So we analyze the player movements and then give them feedback based on their actual pose and what the ideal pose is. It is used in robotics and AR filters also. So how it works? So initial detection, the system uses object detection model to find out and localize the target object in the first frame. So this creates the initial bounding box that tracking algorithm will follow. Then feature extraction happens. So the tracker extracts distinctive features that characterize the objects, and these features are then stored in the database. Then frame to frame tracking happens. So as the frames change, it is again it tries to see where the object is now in the new frame, and then it is able to identify the movements of the object. And when tracking confidence drops, the model redetects the object, corrects its trajectory, reassigns the ID if needed. So there is update and correction cycle. Next, we come to pose estimation. This is again a separate area of computer vision. So it is a powerful technique which identifies the position of key body joints to map human movement and posture. It creates a digital understanding of how our bodies move through space by tracking critical anatomical landmarks. Upper body, head, shoulders, elbows, and wrist. Core, which consists of spine alignment and torso positioning, and lower body, hip, knees, and ankles. The output is a skeleton like structure which represents human posture with remarkable precision. This digital skeleton enables machines to understand not just where a person is, but now they are moving their body alignment and techniques. So, pose estimation consists of detecting the body structure, joint angles, and movement patterns. Reliable analogies: a dance instructor watching your body alignment. So, a dance teacher doesn't just check attendance, they carefully observe how your hands move through space, whether your feet are properly aligned, and then gives you the feedback to correct the angles. So, pose estimation functions exactly like the attentive teacher, which continuously tracks your body joints to understand and evaluate your movements. Then, motion capture without the suit. In Hollywood, actors wear motion capture suits covered with reflective markers, which are placed on key joints. And then, multiple cameras track these markers to animate digital characters. So, pose estimation achieves the same result automatically. A fitness coach correcting your form. So, when you perform squats, an experienced coach checks various angles of how you are doing it to prevent you from injury. The pose estimation does the same thing. It extracts these same biomechanical details but numerically, objectively, and then gives you the quantifiable feedback, which will keep on improving over time. So, how it works? So, first, image pre-processing is done. So, you resize the image to optimal dimensions and then pre-process it. Then you do person detection. You identify where the actual person is in the image using YOLO model. Once person detection is done, then you do key point heat map generation. So each joints and of the upper body, core, and the lower body are connected, and a skeleton construction is done later, which shows the pose of the person at that particular frame. And then there is pose tracking across frames. So each video is converted into frames, and in each frame, the pose is tracked as to how the pose was in the first frame, then how it changed. And based on this temporal features, we are able to get the exact way or exact movement with the person is done across the frames. And then on this feature extraction and analysis is done to calculate the meaningful metrics, which can then be used to compare with the gold standard video. So best example of post detection is AI cricket virtual coach, which is revolutionizing the cricket training through computer vision and machine learning. So there are gold standard videos taken from the cricketers, and then on that videos pose estimation is done and the numerical metrics are saved in database. Now whenever there is a guy playing in a village, and if he uploads his video on an app, then over there pose estimation of his video is done and it is compared with the gold standard video of Sachin Tendulkar, and then both of them are checked, and then feedback is given as to where he is going wrong, what angle he has to take, or how he has to change himself to come to perfection. So just by using a mobile smartphone from a village, the person can get professional training from Sachin Tendulkar. So the pipeline over here is you take video input, player uploads the bowling batting footage from any mobile camera. Then there is pose extraction. So on this, there is a pose extraction which is done. So the frame by frame skeleton key points are extracted, tracking 17 to 33 body joints throughout the motion. Then signal processing helps in noisy data removal, and deriving biomechanical features, including angle, speeds, timing. And then expert comparison is done with the gold standard videos. And based on that, you come to know where the mistakes are. And hence, based on those mistakes, generate comprehensive scoring across multiple dimensions. And then it is converted into numerical language coaching tips, prioritize drills, and actionable improvement plans. So this is one of the latest in computer vision and is taking a lot of attention from all the sports fraternity, and a lot of investment is happening in developing such models. So various pose estimation models are, so basically first we have the pose estimation model which estimates the pose and detects 1733 key points. Then we have temporal tracking. So we need consistent tracking across the frames. Hence, Kalman filters, optical flow algorithms, and built-in temporal tracking ensure that across frames we come to know how the pose is changing with time series position data. And then signal smoothing is there. So pose data is inherently noisy due to camera shake, lighting variations. So all the algorithms like Savitri, Gole filters, Kalman filtering is used to clean the data. Then we normalize the coordinates. So this actually helps across the cricket ecosystem. For players, they have always available coach accessible. For coaches and academics, they are able to train hundred of players simultaneously, acts as an intelligent second coach, providing detailed analytics. For leagues and cricket boards, talent identification and scouting based on objective technique metrics, injury risk monitoring by flagging dangerous bowling actions early. So it we are able to, if we are able to deploy this across the nation, we can find the talent in every nook and corner of India. And for broadcasters and fans, we can engage them on screen by showing the skeleton overlays during live matches, head to head comparison, new fan engagement, and interactive coach mode. Now we come to image generation. So till now we were looking at all the possibilities of processing an image and finding out where the object is or what are segments are there. Now we move one step ahead and we generate a new image. So image generation in itself is a groundbreaking branch of computer vision where machines transcend mere understanding to create entirely new images from scratch, visuals that have never existed in the real world. And this capability has led to a big shift, and we are able to generate synthetic data, synthetic videos. So AI can now envision and produce novel scenes. Synthetic datasets are generated, which are diverse datasets for training other AI models, overcoming data scarcity and privacy concerns. Design products and art. From innovative product design to compelling artwork, AI can help as a digital creative assistant. You can restore old or damaged images, filling in missing details and improve quality with remarkable accuracy. So this is where image generation helps. So how it happens? So it learns the visual patterns from millions of images and understands the color, shape, textures, and semantic relationship. In advanced model like diffusion network, AI learns how to systematically reverse a noise process to reveal an image. Then there is guide generation, text prompts or other images or specific conditions to direct AI towards a desired output. And the model iteratively refines its output, sampling from its learned distribution until a high quality image is produced. Algorithms which power image generation. So, generative adversarial network. This is the deep learning algorithm or deep learning area where you are able to generate new content. You are able to generate new images. So there is a generator and a discriminator. The generator keeps on creating synthetic images, and discriminator tries to give it feedback and tell whether it is fake or real. And this competition will drive the generator to produce increasingly realistic images and gains excel in face generation, fashion design, and synthetic data generation. A time will come when the discriminator will not be able to distinguish between the original image and the generated image, and that is where the final image is produced. Then there are diffusion models, stable diffusion, Delhi, mid journey. These start with random noise and gradually remove it, guided by text or image prompt to produce exceptionally detailed and realistic output. Then another technique is variational autoencoders. VAEs learn compressed representation of images, then reconstruct them. So they are vital components within larger systems for tasks like image compression and creating smooth variations. Image generation is the future of computer vision because here you are able to generate new data. Your dependency on data reduces. It empowers creativity at scale, provides tools for artists, designers, and innovators to create visuals rapidly, expands the training dataset. You can augment the dataset. So if you have only 100 image of Aadhaar card, you can go to 1000. You can generate synthetic images, bridges the imagination and reality, turns abstract concept and textual description into tangible visual output, enabling unprecedented prototyping and visualization. And it is the foundation for future technologies. So AR, VR, robotics, advanced simulation, all of these will use image generation. Essential image processing techniques. So image pre-processing is a critical step because the more you refine the image and then give it to the model is able to do predictions in a better way. So there are various techniques of doing image pre-processing. One is image resizing, scaling image to consistent dimensions. So basically you make it uniform. Image normalization, adjusting pixel value and converting it to between 0 to 1 rather than higher values. Then there is noise reduction. There are techniques like Gaussian blur, median, and bilateral filters, which remove unwanted grain or visual distortions. Denoising an image actually enhances and improves the accuracy of algorithms. Grayscale conversion is there, where you convert RGB image into a grayscale so that it can be easily used for faster computation. Thresholding is there. So this is the binarization process. It converts grayscale images to pure black and white using a defined threshold, Otsu thresholding. Then we have edge detection, where algorithms like Canny, Sobel, Privet, they are able to detect the boundaries of a object for shape recognition, segmentation, and object detection. There are some advanced techniques for feature extraction, which are known as morphological operations. So erosion, dilation, they can manipulate image shapes. They are used to remove noise, strengthen object boundaries, and fill gaps or holes within the objects. Histogram equalization is there. It redistributes image brightness to improve contrast, making low contrast image more discernible and features more visible. Then we have image cropping, ROI extraction. By selecting only the important region of interest, cropping removes irrelevant background information. This not only speeds up processing but also increases accuracy by ensuring the model focuses exclusively on useful regions, boosting model robustness and feature isolation. So, your data augmentation actually helps because data augmentation helps you to generate more images just by using transformations like rotation, flipping, zooming. So, if you have 500 pen cards and if you have only 10 Aadhaar cards, then you cannot give it to the model because both dataset are not at equal level. So, this technique increases the Aadhaar dataset from 10 to 500 by generating new Aadhaar cards by using flipping, zooming, brightness variation, and hence it helps in class balancing. You can convert images across color spaces, so it helps to isolate specific color features, highly beneficial for tasks like skin detection, plant disease detection, and defect identification, as it provides better handling of illumination changes and highlights crucial chromatic information. refining visual details and correcting distortions. So you have image sharpening. It enhances the edges using kernels like lep, cane, or unsharp masking, clarifies boundaries and improved feature extraction. It is useful in applications requiring fine details such as satellite imaging, medical imaging, geometric transformations. These transformations include rotation, translation, and perspective correction, which are used to rectify camera distortions. So all these are the various techniques which are used on images before they are fed to the model. Now, what is image EDA? Image exploratory data analysis. It is the process of identifying how the image is, what are the characteristics before we actually give it to the model. So during EDA, we try to investigate several fundamental aspects of the dataset. It includes examining data distribution patterns across classes, identifying quality issues like noise, detecting class imbalance, which could lead to bias in the training, and analyzing variations in lighting conditions. So visual inspection and image properties is done. Image dimensions are checked. Then we check the color and lighting analysis, color distributions. Brightness and contrast is also checked. The key steps in EDA are check class imbalance. If there is imbalance, then do data augmentation to bring all classes at the equal level. To detect the outliers and anomalies, so problematic images are excluded from the overall dataset. Analyze feature correlation. So we examine the texture distribution, shape features to identify how they are related and if there is any opportunity for dimensionality reduction. Data augmentation helps to create more data from whatever data we have, and it actually helps to remove the class imbalance. So minority classes are augmented and brought to the same level. If rotations matter for your application, incorporate rotation augmentation. So EDA basically helps in all these processes. Where EDA is used. So in manufacturing, you identify defect patterns before designing detection algorithms. And before actually giving data to the algorithm, you try to understand your data. In healthcare also, you standardize resolutions of medical scans from different equipments and identify anomalies in X-ray or MRI. In retail, you spot mislabeled product images that would confuse recommendation systems. In agriculture, you understand visual variance in crop disease presentation and spot environmental pattern. In finance, detect poorly scanned identity documents which require recapture and identify orientation issues. So these are the 6 transformative business cases for computer vision. Aadhaar masking on premise, where you can develop a model, computer vision model, and end-to-end system which can do Aadhaar masking on your own premise. The data did not leave your organization. Then classifying the documents. So you can automatically classify the documents as PAN card, Aadhaar card, driving license, passport without any manual intervention. Then you can use it for visual quality inspection. So high quality images can be parsed in real time through the algorithms to identify if they have defect or they don't have defect. In autonomous driving systems, object detection and a lot of other computer vision capabilities are used to identify and take action based on what objects lies ahead. Then we have military drone applications and cancer detection and diagnosis. These are some of the jargons: pixel resolution, channels, grayscale image, feature map, convolution, stride, padding, pooling, CNN, backpropagation, activation function, overfitting, data augmentation, object detection, bounding box, segmentation, semantic segmentation, as well as instance segmentation. Then we have pose estimation, OCR, image embeddings. So most of these we have covered in our this training. GAN is there, diffusion model, autoencoders, variational encoders, Normalization is scaling the pixel values to standard range of 0 to 1. VIT transformer, vision transformer, image augmentation pipeline. Model drift, when a deployed CV model loses accuracy due to changes in environment. Inference is the process of running a model to make predictions on new image. So that's all about computer vision. It's a very vast field, and I have explained all the concepts which are involved in computer vision. You can do some POCs on each of the concepts and keep watching out for my videos, because we will also be going and exploring the business cases where I will show you how to actually do all of these, image classification to image segmentation. Thank you, and see you in the next video.